presentation with the code ID code 4612 with Vitaly Zhugalkov. Intelligent control of electric flywheels, motors, units. Vitaly, are you online?
Hello, dear colleagues. Hello. Now I start the presentation. 1 minute, please.
Yes. We have 15 minutes.
Well, dear colleagues, let us bring your attention a report on topic intelligent control of electric flywheel motors unit. This report was prepared by Professor Anatoly Kulik, Dr. Konstantin Dervechev, Dr. Vitaly Zhulgakov, and lead engineer Vasil Petrenko, all from National Aerospace University, Kharkiv, Ukraine. And the report presents the results of theoretical and experimental studies of the fundamental possibility of joint use of deep diagnostics and flexible recovery procedures to ensure rational control of the operability of model unit of flywheel electric motors under various destabilizing effects. A rational control system has the following properties. Control is performed under conditions of uncertainty of destabilizing influences. Control is formed on the basis of knowledge about the properties of the elements of the system and possible destabilizations. In the process of control, deep diagnostics of the causes, places, and type of destabilizations is performed. And formation of control by diagnosis occurs as a decision-making process and includes the recovery of operability of the control system. So such properties of the rational control system allow us to consider it as a kind of intelligent control system. First of all, we want to present the complex approach to provide fault tolerance of rational control system. To describe abnormal models in accordance with the provision of automatic control theory, appropriate mathematical models are needed that connect the causes of destabilization with the consequences. Such models are called diagnostic models, and they have received appropriate development in a number of studies. So to develop effective diagnostic models, we should perform such steps as failure detection, search of failure location, identification of failure class, and identification of failure type. As a result of these procedures, we have a diagnosis with required depth. Then the next stage is development the restoration support. In this way, we should choose different approaches, such as synthesis of signal tuning algorithms, synthesis of parametric tuning algorithms, control of algorithms configuration, and control of equipment configuration. So the further research based on this structure. First of all, fundamentals of rational control approach were considered on the base of block diagram of the system of rational control, or system which performed control by diagnosis. So to the regular structure of the automatic control system, the unit such as diagnostic unit is added. And we divided the structure of control system to two parts or two subsystems as rational control object, RCO, and rational control device as RCD. and diagnostic unit is a hardware and software part inside the rational control device. So the diagnostic unit is the key element in presented block diagram. The purpose of diagnostic unit is to form a diagnosis of the rational control object. For this, it is required to detect the appearance of destabilizing effect, localize and identify it by searching for a place and defining a class and a type of the failure. So, electric flywheel motors, or EFM, are used to create control targets relatives to the center of mass of spacecraft. Electric flywheel motors belongs to the class of inertial actuators of the spacecraft, which ensure the redistribution of the angular moment between the rotation rotor and the body of the apparatus. There are several redundant EFM placement structures. A pyramidal structure presented at the slide was selected for implementation and further research. This configuration was developed by General Electric Company. The block diagram of the pyramidal placement shown in the slide includes 4 electric flywheel motors, 4 flywheel angular velocity centers, or Tahoe TG1, TG4, and 3 angular sensors. The external view of the experimental stand with the EFM prototype unit placed in a gimbal is shown at the slide 5. The platform includes 4 electric flywheel motors placed according to the pyramidal structure. The platform is fixed in the 3-stage gimbal frames and can simulate the angular movement of the spacecraft. For each EFM of the prototype unit, a system is formed that provides both the control of the kinetic moment and the stabilization of the operability under destabilizing influences. Functional diagram of the digital system of rational control of EFM operability for one channel is shown in the slide. For the formulation of algorithms for diagnosing and restoring operability, mathematical models are required that reflect the transforming properties of the functional elements of the system. The construction of mathematical models is based on experimental static and dynamic characteristics of the units. A series of experiments were carried out on this experimental stand, and the appropriate characteristics of the elements were obtained. In the space of continuous states, the transformation of temporal signals into RCO can be represented by a system of vector matrix equation. After the appropriate transformation, the following system of discrete equations was obtained. Diagnostic models are the mathematical descriptions linking the cause of destabilization with its consequence. For the formation of diagnostic model, it is necessary to identify destabilizing effects that disrupt the operability of RCO. The experimental stand has the ability to simulate 14 types of destabilization. For example, for a power amplifier, the set of destabilization consists of the such types as reduction of transfer factor, positive and negative drift, and break at the input wire. For electric motor, the set includes 3 types of destabilization, such as reduction in transfer factor, increasing the time constant, and break in the control circuit. And for Tahoe, the set includes such type of destabilizations as a reduction in transfer factor, positive and negative drift, and break at the output wires. Really, the set of destabilization is not full, but it is a main destabilization effects which considered in the work. So for each of 14 types of destabilization disrupts the operation of RCO. To detect this fact, the reference model of the operation is used in the form presented in equation 4. With this model, a deviation signal may be calculated or generated according to the formula 5. Then the partial diagnostic model of elements of rational control object was created. For example, for power amplifier, such equation presented in the formula 6. And for electric motor, the diagnostic model will be in the forms such as 7. And for Tahoe, such diagnostic model as formula 8 will be were created. And such type of diagnostic model were designed for each of 14 types of destabilizations. So, according to the main provision of rational control, destabilizing effects are one-time undefined events. So, diagnosis is able only with the help of the procedure for searching for the specific type of destabilizing effect according to its scenes. The most adequate for the formation of scenes of destabilizing effects, as evident by the result of experimental studies, is the production model. In the production model, knowledge is represented by a set of rules, if-then, and to form the rules, two-valued predicate equations obtained from the corresponding diagnostic models are used. The procedure for diagnosing based on the scenes of the reason for the destabilization of RCO is formed in the form or dichotomous tree, presented at the next slide. So this dichotomous tree is used for searching of type of destabilizing influences in RCO. And with the help of diagnostic model, the arguments of the predicate equations are formed, from which the procedure for searching of the type of destabilization of RCO is constructed. First, the procedure starts with the predicate shown as equation 9. And in this predicate, we use some parameters as deviation of the signal from ticket generator because it is the main measuring device in the system. Tolerance for deviation, number of measurements, and confidence factor proposed by experts. To determine the RCO fragment subject to destabilization, the following predicate is calculated as expression 10. And for example, for power amplifier, scenes of types of destabilization can be detected using the following predicates, such as expressions 11. So the set of such predicates were formed for all of 14 types of destabilizations considered in this work. The dichotomous tree ends with leaves, which contain the estimated values of the parameters that characterize the magnitude of destabilizing effects. Estimated values are obtained from the corresponding diagnostic models after arithmetic mean processing. So for a power amplifier, we obtain such parameters which characterize the magnitude of destabilizing effects presented in expressions 12. Both for electric motor and tachygenerator, such expressions as CETIN were obtained. And in such way, for all parameters, these expressions were designed. So after the forming all parameters for dichotomous tree, we can develop the steps for restore repairability. So to restore repairability, redundant tools and means of putting them into operation, algorithms and programs for compensating for the consequences of destabilizing effects are needed. The experimental stand implements the simplest version of the use of excess funds, when each type of destabilizing effect uses its own tool for compensation. So, for example, for power amplifier, under the action of destabilizing effect, the reduce of transfer factor, its influences may be compensated by means of signal adjustment. And according to the expression 14, we can calculate the additional part of control signal to compensate this destabilization. For such type of destabilization as positive or negative drift, we can calculate the control signal, which includes the additional part for compensation, the drift according to its positive or negative value.
Sorry, excuse me, please go ahead quickly because we have time scheduled.
Well, I finished now. And in such way, we can calculate the additional control for electric motor transfer factor, and for such destabilizing effect is increase of constant time. So the approach is similar for all other destabilization parameters. And during the experimental research, we developed algorithmic aid software for the stand and perform the research for compensation of different types of the influences, all 14 types. For example, the compensation of the reduction in power amplifier gain is shown in the slide, and the main issue is that we can compensate by means of proposed algorithms. We can compensate the destabilization during the transient process, which is shown at the graph. And in the end of the report, short conclusions. So the results of the carried out studies confirmed the fundamental possibility of deep diagnostic of the EFM control channel during the transient process, and the possibility of restoring operability before the end of transient process when simulating a number of destabilizing effects. The obtained results open up the opportunity to move on to solve new problems of forming a compact modular software structure for diagnosing and restoring of the operability of the entire EFM unit. And it also seems promising to expand the capabilities of diagnostic procedures with the necessary means of using signals from the spacecraft angular position sensor. Such use will expand the set of diagnosis destabilizing effects and increase the efficiency of obtaining a diagnosis. So thank you for your attention.
Thank you very much, Dr. Vitaly Julgakov, for your interesting presentation. We have very short time for discussion, for questions. Any questions, please? I have short questions. The title of your presentation is Intelligent Control. And decision which you presented based on 3 of decisions, yes, but this decision 3 is deterministic. And so my question is, where we talk about intelligence control, based on your model, your algorithm, and so on. Thank you.
Yes, thank you for the question. And I want to return to the beginning of our presentation. And we studied this question, and according to the recommendations of Institute of Engineers of Electronic and Electricity, the features of intelligent control systems based on the some parameters or some characteristics of the control system, and these features are uncertainty, operation under uncertainty of parameters, operation on the basis of knowledge, using of diagnostics in the operation process, and using of decision-making approaches. So we think that all of these features are used maybe in some decreasing, but used in the proposed approach. So we assigned the structure of the system and proposed algorithms as a kind of intelligent control systems. Of course, it's not a strong criteria, but such approaches are used in the operation of proposed system.
Okay, I understood that in this case we talk about cumulative effects, yes, and
Yes,
as
yes.
factor we can say the intelligence control. Thank you. Thank you very much. I don't see other questions. Thank you.
Thank you. Thank you for your attention.
Dear colleagues, let's go ahead. We have a lot of presentations, and I would like to ask all of you about time schedule. Let's not more than 12 minutes. We would be better if we will time for more wide discussion. Okay. Our next presenter.